So let's get started. Today, I'm going to be talking about learning from human feedback. I wrote reinforcement learning from human feedback because that's what a lot of people talk about nowadays. But actually, there's other methods of learning from human feedback. So first, I'm going to be talking about the ways we can get human feedback for the generations of models, and mostly focus on generation tasks because generation tasks are harder than like classification tasks that we deal with normally. So I'll spend a fair amount of time talking about how we do that, and then after I talk about how we do that, we'll move into how we actually learn from that signal. So normally what we've done up until this point is maximum likelihood training. This is just an overview slide. So what we want to do is we want to maximize the likelihood of predicting the next word and the reference given the previous words, which gives us the loss of the output given the input, where the input can be the prompt, the output can be the answer to the output. But there's lots of problems with learning from maximum likelihood. And I'm going to give 3 examples here. I think all of these are actually real problems that we need to be worried about. So the first one is that some mistakes are worse than others. So in the end, we want good outputs, and some mistaken predictions can be a bigger problem for the output being good. So to give an example, let's say what we actually wanted from like a speech recognition system or a translation system or something like that is please send this package to Pittsburgh. If I write, please send a package to Pittsburgh, then this is not a huge problem. If I write, please send this package to Tokyo, then that might be a big problem because the package you wanted to come to Pittsburgh goes to Tokyo instead, and you might not want that to happen. You might also have it say bleeping, send this package to Pittsburgh instead of please, and that would be a problem in a customer service system, right? Because your customer would leave and never come back. So determiner like this is not going to cause a huge issue. Messing up other things is going to cause a larger issue. But from the point of view of maximum likelihood, all of these are just tokens. And messing up one token is the same as messing up another token. So that's an issue. Another problem is that the gold standard in maximum likelihood estimation can be bad. It can be like not what you want. And corpora are full of outputs that we wouldn't want a language model reproducing. So for example, toxic comments on Reddit, disinformation. Another thing that a lot of people don't think about quite as much is a lot of the data online is automatically generated nowadays. For example, from machine translation, a lot of the translations online are from 2016 Google Translate. When Google Translate was a lot less good than it is now. And so you have like poor quality translations that were automatically generated. A final problem is something that's called exposure bias. And exposure bias, basically what it means is MLE training doesn't consider the necessity for generation, and it relies on gold standard context. So if we go back to the MLE equation, when we're calculating MLE, this y less than t is always correct. It's always a good output. And so what the model does is it learns to over-rely on good outputs. And one example of a problem that this causes is models tend to repeat themselves over and over again, for example, when you use some generation algorithms. And the reason why this happens is because in a gold standard output, if a word has appeared previously, that word is more likely to happen next. So like if you say, like I am going to Pittsburgh, you're much more likely to say Pittsburgh again in the future because you're talking about Pittsburgh topically, it's coherent. So what you get is you get MLE trained models saying, I'm going to Pittsburgh, I'm going to Pittsburgh, I'm going to Pittsburgh, I'm going to Pittsburgh. You've probably seen this before at some point. And so exposure bias is basically that the model has never been exposed to mistakes in the past, and so it can't deal with them. So what this does is, if you have an alternative training algorithm, you can fix this by generating a whole bunch of outputs like scoring some of them poorly and penalizing the model for generating poor outputs. And so that can fix these problems as well. Any questions about this? All good? Okay, cool. So now I'd like to get into how we measure how good an output is. And there's different ways of doing this. The first one is objective assessment. So for some tasks, or for many tasks, there's kind of objectively a correct answer. There's also human subjective annotation, so you can ask humans to do annotation for you. There's machine prediction of human preferences. And there's also use in another system, in a downstream task. So the way objective assessment works is you have an annotated correct answer and match against this. So like if you're solving math problems, answering objective questions, and you can pick any arbitrary example. You can pick your classification example from like your text classification tasks. An even clearer example is if you have math problems, there's kind of objectively one answer to any math problem, and there's no other answer that could be correct. So this makes your life easy if you're handling this type of problem, but of course, there's many other types of problems we want to handle that don't have objective answers like this. So let's say we're handling a generation task where we don't have an objective answer. In this case, kind of one of our gold standards is human evaluation. So we might have a source input, like a prompt or an input text for machine translation. We have one or several hypotheses, and we ask a human annotator to basically give a score for them or do some sort of other annotation. And the different varieties of annotation that we can give are something called direct assessment. So direct assessment is a term that comes from machine translation. So you might not see it used lots of other places, but it's basically just give a score directly to how good the output is. So you can say, like, if you say, please send this translation is please send this package to Tokyo, we give it a score of 2 out of 10 or something like this. So the question here is like, what does, like, let's say I gave a score of 2 out of 10 for please send this package to Tokyo. What score should I give for please send a package to Tokyo? Anyone have any ideas? The correct answer is please send this package to Tokyo. 8 out of 10. Yeah. But you might disagree on that, right? It's kind of like subjective. One of the difficulties of direct assessment is giving a number like this is pretty difficult if you don't have a very clear rubric and very skilled annotators. And it's hard to get consistency between people when you do this. So the advantage is it kind of gives you an idea of how good things are overall, but the disadvantage is it's more difficult to annotate and get consistency. Another thing that I should point out is often scores are assigned separately based on desirable traits. So we don't necessarily just say how good is it, we say how fluent is it? Like, is it fluent English? In translation, there's a concept called adequacy, which is how well does the output reflect the input semantics? And if you're assessing translation systems, actually it's common to assess fluency without even looking at the input, because then you can just say how fluent is it. But for adequacy, you definitely need to understand the input. So you need to be a bilingual speaker to be able to assess that. Factuality. And so factuality is tricky. It can either be factuality grounded in a particular input text, in which case the facts would have to be, things that were said in the input, or it can be just kind of, is the statement factual in general, in which case you need to go online, you need to search for things and like check whether the statement is factual or not. Other things are like coherence. Does the output fit coherently within the larger discourse? And there's many, many other ones of these. This is also task dependent. So like the things you will evaluate for machine translation are different than the ones you would do for dialogue, which are different than the ones you would do for a general purpose chatbot, which is different than the things you would do for summarization, for example. So if you're interested in doing something like this, then I definitely encourage you to look at what other people have done for the tasks you're interested in previously, and find out the different types of traits that you'd like here. Any questions about this also? Okay. The next type of feedback is preference ratings. And so this is basically what you do is you have two or more outputs from different models or different generations from an individual model. And you ask a human which one is better, like is one better than the other, or are they tied? And so in this case, you might have, please send this package to Tokyo, please send a package to Tokyo. We might disagree on how like good or bad each of them are, but I think most people would agree that this one is like, despite the fact that it got this wrong, the second one is better than the first one. So this is a little bit of an easier task. It's easier to get people to annotate these things consistently. However, it has the disadvantage that you can't really tell whether systems are really good or really bad. So let's say you have a bunch of really bad systems that you're comparing with each other. You might find that one is better than the other, but that still doesn't mean it's ready to be deployed. Or if you have a bunch of really good systems, they're all basically, you know, very, very similar to another, but one is like slightly more fluent than the other. You might still get a similar result. And so that also makes it, you know, a little bit difficult to use practically in some ways. I didn't put it on the slide, but there's another way you can kind of get the best of both worlds, which is side-by-side assessment. And side-by-side assessment, basically what you would do is you would say, please send this package to Tokyo, please send a package to Pittsburgh. Give each of them a direct score, but you can use decimal places and you can't use the same score for all of them. And so it's like 5.00 and 4.99 out of 5 or something like that. Like you like one slightly better than the other or something like that. So there are ways to kind of get best of both worlds if you're interested in doing that. So one other problem with preference rankings is that there's a limited number of things that humans can compare before they get really overwhelmed. So if you say, I want to rate 15 systems or 20 systems with respect to how good they are with respect to each other, it's going to be impossible for humans to come up with a good preference ranking between them. And so the typical way around this, which is also used in things like the chatbot arena by LMSys and other things like this, is to use something like an ELO or true skill ranking. And what these are things that were created for the ranking of like chess players or video game players or other things, where they like battle against each other in multiple matches, pairwise, and then you put all of the wins and losses into these ranking algorithms, and they give you a score about how good like each of the players are. So if you do something like this, you can get basically a ranking of systems despite the fact that you only did pairwise assessments. So these are also a good thing to know about. A final variety of human feedback that we create is error annotation. And this can be useful for a number of reasons. But basically the way it works is you annotate individual errors within the outputs. And one thing I should mention is that I'm giving a lot of examples from machine translation. I feel like machine translation has been doing evaluation of generated outputs for a lot longer than a lot of other fields of NLP have, and therefore their methodology is more developed than a lot of other fields. But a lot of these things can also be applied to other tasks as well. But anyway, getting back to this, there's something for machine translation called multidimensional quality metrics. And the multi-dimensional quality metrics, basically what they do is they annotate spans in the output, where each span in the output is given a severity ranking of the error, and it's given a type of the error. And there's about 8 different types of errors. Like this doesn't violate, or this violates linguistic conventions of using the word this instead of here, by using the word instead of this here. And then this is an accuracy error because it's not accurately conveying the output. And then this error is minor. This error is major. And then there's also like severe versus major, but minor and major is a more important distinction. So the advantage of this is a couplefold. Number one, it gives you more fine-grained feedback in that you can say, okay, this system has a lot of accuracy errors. This system has a lot of linguistic conventions errors. It also can be more consistent because if you just say to people which output is better or what is the score of this output, people have trouble deciding about that because it's a more subjective evaluation. But if I say, is this word correct? It's a little bit easier for people to do. So you can get more consistent annotations here. The problem with this is this can be very time consuming. So, obviously you need to go through and annotate every single error. If it's for long outputs or something, then that can be a problem. So anyway, these are just three ways of collecting human feedback. And then there's an alternative, which is automatic evaluation of outputs. And there's a bunch of different ways we can do this. The basic idea here is we have a source. We have a couple hypotheses, and we have an automatic system that generates outputs like scores. And we optionally have a reference output. So the reference output is a human-created gold standard output with respect to how good that, with respect to like what the output should be in an ideal case. And basically, the goal of automatic evaluation is to predict human preferences or to predict what the human scores would be. Because still, at this point, we mostly view what humans think of the output to be kind of the gold standard. And this is called a variety of things depending on what field you're in. In machine translation and summarization, it's called automatic evaluation, also a lot in dialogue. If you're talking about people from reinforcement learning or other things, or chatbots or things like that, a lot of people, or like AGI or whatever, a lot of people call it a reward model. Because that specifically comes from the point of view of like learning from this feedback. But essentially, they're the same thing from my point of view. They're trying to predict how good an output is and how much you should reward the model for producing that output. So there's a bunch of different methods to do this. I'm not going to cover all of them. I'm just going to cover three paradigms for doing this so you know where to look further if you're interested in doing these things. The first one is embedding-based evaluation. And the way embedding-based evaluation works is usually it's unsupervised calculation based on embedding similarity between the output that the model generated and a reference output that you have created. So, sorry, this is very small, but we have a reference here that says the weather is cold today. And we have a candidate that says it is freezing today. So this is probably, like a good, a reasonably good output. And we run this through some embedding model. It was called BERT score. And so of course you can run it through BERT, but basically it can be any embedding model that gives you embedding for each token in the sequence. And so there are 5 tokens in this sequence, 4 tokens in this sequence. You get 5 tokens and then 5 embeddings and then 4 embeddings. You calculate pairwise cosine similarity between all of them. And this gives you a cosine similarity matrix. And then you take the argmax, or you take the maximum similarity along either the rows or the columns. And here the rows correspond to tokens in the reference. And because the rows correspond to tokens in the reference, how well you find something that is similar to each of the tokens in the reference is like a recall-based metric. Because it's saying how many tokens in the reference have a good match in the output. And then if you look at the columns, if you look at the max in the columns, this is like a precision-based metric because it's saying how many of the things in the output are similar, have a similar match in the reference. So basically you can calculate recall and precision over all of the tokens, and then feed this into something that looks like F measure. And you can also use TF-IDF weighting, like what I talked about in the RAG lecture, to upweight low frequency words, because low frequency words tend to be more content words. And going back to my example, if you make a mistake from Pittsburgh to Tokyo, that's going to be more painful than making a mistake from this to up. So actually, if you were paying close attention to the RAG lecture, this looks really similar to the Colbert retrieval objective that I talked about in the RAG lecture. I don't think it's a coincidence. They both came out around the same time, so people were thinking about the same thing. But this is one method that's pretty widely used. The BERT score code base is also really nice and easy to use. So if you want to try it out, feel free to take a look. Cool. The next one I'd like to talk about is a regression-based evaluation. And the way this works is this is usually used in a supervised setting. So what you have to do is you have to calculate a whole bunch of like actual human judgments. And usually these judgments can either be direct assessment, where you actually have a score, or they can be pairwise judgments. And then if you have direct assessment, you use a regression-based loss like minimum squared error. If you have pairwise, you use a ranking-based loss that tries to upweight the ones that are higher scoring and downweight the ones that are lower scoring. One typical example of this is Comet, which is, or has been at least for a very long time, the state of the art in machine translation evaluation. And the reason why it works so well is because we have a bunch of evaluations for machine translation. They've been doing evaluation of machine translation systems for years, and you can use that as lots of supervised training data. So basically, you just take these evaluation data, you have human annotations, you have the output according to a model like Comet, you calculate the difference between them, and you update the model parameters. The problem, this is great if you have lots of training data. The problem with this is for a lot of tasks, we don't have lots of training data. So, training these is a little bit less feasible. And now recently, what we have been moving into is QA-based evaluation, which is basically where we ask a language model how good the output is. And so Gemba is an example, one of the early examples of this for machine translation evaluation, where they basically just ask a GPT-4, like score the following translation from source language to target language with respect to the human reference on a continuous scale from 0 to 100, where the score of 0 means no meaning preserved, and the score of 100 means perfect meaning and grammar. You feed in the source. You feed in the human reference optionally if you have a human reference, and then you feed in the target, and you get a score. And so this works pretty well. This can give you better results. Especially if you have a strong language model. The problem is it's very unpredictable whether this is going to work well, and it's very dependent on the prompt that you're using. So right now, a lot of people are using GPT-4 without actually validating whether it does a good job at evaluation. And the results are all across the board. It can be anywhere from very, very good to very, very bad at evaluating particular tasks. So I would be at least a little bit suspicious of whether GPT-4 is doing a good job evaluating for your task, especially more complex tasks. I would especially be suspicious if you're doing any of the two following things. Number one, if you're comparing GPT-4 or any model against itself in another model, because GPT-4 really likes GPT-4. It really likes its own outputs. And there are papers, sorry, I don't actually have the references here, but I can follow up if people are interested. But there are papers that demonstrate that GPT-4 likes it, its own outputs more than others. Also, if you're explicitly optimizing the outputs using RLHF, there's something called Goodhart's law, which is basically anytime you start optimizing towards a metric, it becomes a bad metric. And that also happens for GPT-4-based evaluations. So if you start optimizing for GPT-4-based evaluations, especially for referenceless metrics that don't use a reference output, then you start basically exploiting the metric. Another thing that you can do with QA-based evaluation is ask about fine-grained mistakes. And so this is a paper by Patrick Fernandez, who's a student who's working with me. And basically what we did is we asked the model to not give a particular score, but actually identify the mistakes in the output. And when we asked it to identify the mistakes in the output, we found that this gave more consistent results. So kind of interestingly, we ask humans to identify individual mistakes in the output. That gives humans more consistent results. It's the same thing for GPT-4. So that's another paper you can look at if you're interested. Cool. So I mentioned that you could or could not trust. Yeah, sorry, go ahead.
Evaluating the output of any model with GPT-4.
Correct. So yeah, basically just what you do is you have the source. Ideally, you'll also have a reference output that was created by skilled humans. And then you put in the target, the output, basically. You have the input, ideally a reference output created by by skilled humans and like hypothesis from the model.
Would we not expect it to be the case that any model will like its own output?
Yeah, I mean, it's a good question, and I don't know if we actually have a very clear empirical evidence of why this is the case. But my hypothesis about this is yes, we kind of would expect models to be more biased towards their own outputs. And the reason why is because essentially, models are within their embeddings, they're encoding when they're in a high probability part of the space and when they're in a low probability part of the space. And like the high probability part of the space is going to be, the high probability part of the space is going to be associated with good outputs. Because like when models are more sure of their outputs, they're more likely to be good. Just because that indicates that like they're closer to the training data that it had and other things like that. So model probabilities are associated with outputs, with good outputs, like just correlated. Separately from that, I believe a model can identify when it's in a high probability segment of the space and when it's in a low probability segment of the space. And because of that, I expect that there are segments of the embedding space where it's more likely to answer yes about something being good or not, and those are going to be associated with high probability outputs as well. And also models are more likely to generate outputs that are high probability according to their model by definition. So all three of those facts together would basically go into a model being biased towards its own outputs compared to the outputs of another model. But yeah, this is a very hand-wavy explanation, but like putting the three together, models output high probability things from their own probability space by definition. Things that are high probability are associated with being good, just because otherwise the model would be outputting garbage. And the final thing, which is more tenuous, is if the model is in a high probability segment of the space, it's more likely to output yes, according to a question of it being good. And I think that's probably true, but I'm not 100% sure about the final one. So. Maybe someone wants to examine that as a final project. It seems like an interesting question. Cool. Were there any other questions about these methods here? Okay. So when I say like an evaluation metric is good or not, what do I mean by this being good or not, or a reward model or whatever else? And basically the way we typically do this is by doing something called meta evaluation. So it's called meta evaluation because it's evaluation of evaluation. And the way we do this is we have human scores and we have automatic scores. And we usually calculate some sort of correlation between the scores. So typical ones are rank correlations like Pearson's correlation or Kendall's tau. And so the more associated the automatic scores are with the human scores, the higher these correlations are going to be. There's other things that you can calculate. So if you're trying to figure out whether a model matches human pairwise preferences, you can just calculate accuracy. So I didn't put that on the slide here, but you can just calculate accuracy of pairwise preferences. You can also calculate the absolute error between the judgments if you want to know whether the absolute error matches. So these are good things to do. If you want to use an evaluation metric, but you aren't sure whether it's good or not, I would check to see whether the authors have done this sort of meta evaluation. If they haven't, be a little bit suspicious. If they have, be a little bit less suspicious, but yeah. How do people do this typically? Usually they create data sets like they use data sets like the WMT shared tasks, or like some eval. But there's also other ways to create, there's also lots of other data sets. But in order to do this reliably, you need a fairly large data set. So it's one thing to be aware of. Cool. Then the final thing, all of the automatic evaluation methods that I talked about now are trying to match human preferences, but that's not the only thing that you necessarily want to do. The final thing that you might want to do is use the model outputs in a downstream system and see whether they are effective for that. So there's two concepts of intrinsic evaluation and extrinsic evaluation. So intrinsic evaluation evaluates the quality of the output itself. And so that would be like asking a human directly about how good is this output. Extrinsic evaluation is evaluating output quality by its utility. And so just to give one example, if you can evaluate large language model summaries through question answering accuracy. And so you can take the output of an LLM and feed it through a question answering model and see whether you're able to answer questions based on this. And that kind of gives you a better idea of whether the summary incorporates requisite information. But if you think about anything an LLM can be used for, usually it's part of a bigger system, so you can evaluate it as part of that bigger system. The problem with this is it's a very indirect way of assessing things. So like, let's say your QA model is just bad. How can you disentangle the effect of the LLM summary versus the QA model? That's not a trivial thing to do. So ideally, like a combination of these two is probably the best way to go about things. Cool. So yeah. Yeah, I wouldn't necessarily say it's harder to do. It might even be easier to do, which is like, let's say, let me see if I can come up with a good example. Let's say you are trying to guess whether someone will be hired at a company or not based on an LLM generated summary of their qualifications for a position or something like that. And actually, maybe this is not a great example because whether you should be doing this ethically is a little bit unclear, but let's say you were doing something like that, just because it's the one example I can think of right now. Whether they will get hired or not is clear because you have an objective answer, right? Whether they were hired or not. Or maybe another example would be like, let's say you want to predict a diagnosis in a medical application based on an LLM generated summary of somebody's, LLM generated summary of somebody's, past medical history and all this stuff. And here you want the LLM generated summary. You definitely want the summary because the summary is going to be viewed by a doctor who will make the final decision. But you also have information about the diagnoses of all the people in your medical system later, because, you know, they went through your medical system for years, and you know later, like through lots of tests and stuff, how they were diagnosed. So you generate an LLM-based summary, and then you predict the diagnosis from the summary. So there, the evaluation of the diagnosis is very clear because you kind of have a gold standard answer. But the intrinsic evaluation of whether it's a good summary or not is not as clear because you'd have to ask doctors whether it's a good and understandable summary. So the extrinsic evaluation might be easier because it's clearer. So there are cases like that. The problem is you would have to have that data in order to be able to do that. Yeah.
Isn't it regards to like evaluation?
Yeah.
I was just wondering, like, typically do you just take the newness, like, if you think about it, like, how do you accommodate the diversity?
Oh yeah, that's a great question. So how do you get these scores here? There's a number of different things. In the WMT shared tasks, what they did is the first thing they do is they normalize by annotator. And what they do is they basically take the z-score or z-score of the human annotator's actual scores, because some people are more harsh than other people. And so what that means is you basically normalize to have zero mean and unit variance. And then after they've normalized to zero mean and unit variance, then I think they average together different humans. So then how do you deal with the fact that humans disagree on things? And I think it's pretty varied. I don't know if there's any gold standard way of doing it, but sometimes you just average. Sometimes you throw away examples where humans disagree a lot, because like you can't get the humans to agree. How could you expect a machine to do well? So I think it is a little bit test dependent. Yeah.
So for code generation, would that have a both intrinsic and extrinsic qualities?
Yeah, so for code generation, I love this example because I've worked on code generation. A lot of people only think about extrinsic evaluation of code generation, or I don't know if it's extrinsic, but only think about execution-based evaluation of code generation, which is like you execute the code, you see whether it passes unit tests and other things like this. But in reality, actually, there's a lot of other important things for code, like readability and other stuff like that. And you should be evaluating those things, but I think a lot of people like kind of ignore that. So there are a few papers that do that, but most of the time people just execute the code and see if it passes unit tests. Cool. Okay. So yeah, moving on to the learning part. So now I'd like to talk about learning. And the first thing I'll cover is error and risk. And so basically, the way we calculate error is we generate an output and we calculate its badness. And so generating the output could be argmax, it could be sampling, it could be anything else like that. And we calculate its badness, which is 1 minus which could be like how bad is the output if you have a badness measure, or it could be 1 minus the evaluation score to calculate its badness. And this is defined as error. And generally what you want to do is you want to minimize error. Because in the end, you're going to be deploying a system that outputs, one thing, and you're going to want that to be as good a thing as possible. But the problem with this is there's no easy way to actually optimize this value especially in a text generation style setting, but even in the classification setting, we can't easily maximize error because if you look at the surface of error, at some point you're going to have a non-differentiable part when you take the argmax or when you do sampling or anything like that. So you're not going to be able to do gradient-based optimization. So what we do normally is we instead calculate something called risk. And what risk looks like is we talked a little bit about minimum base risk for decoding, but this is for training time. And what it looks like is it's essentially the expected error. of the output. And the expected error of the output includes a probability in the objective function here. And that probability is differentiable, basically. So we can easily do gradient-based optimization from it, through it. The problem with this is it's differentiable, but for text generation, for example, the sum is intractable because we have a combinatorially large number of potential outputs. Because, you know, if this is, we've talked about this before, but if this is like length, you know, 50 and we have a 30,000 vocabulary, that's 30,000 to the 50 possibilities. We can't take a sum over that many possibilities. So minimum risk training tries to minimize risk. Reinforcement learning, also many of the models, especially policy gradient models, are trying to minimize risk as well. So, but the reason why I wanted to talk about risk first is because this is very simple to get to from the point of view of like all the things that we've studied so far. So I think it's worth talking about that. One other thing that I should mention about is, or no, sorry, I'll talk about that later. So when we want to optimize risk, what we do is we sample in order to make this tractable. So a very simple way to minimize risk is instead of summing over all of the possible outputs, we sum over a small number of possible outputs and we upweight. And we normalize to make this all add up to 1. And so this normalizer here is basically the sum over all of the probabilities that we have on the top part here. And these samples can be created either using sampling or n-best search. We don't need to have, from the point of view of doing this sort of minimum risk training, the kind of correct way of doing this is sampling using ancestral sampling, like we talked about before, and in minimizing the output based on the samples. But the problem with that is, as many of you also might have seen when you were sampling from your language model from assignment 1, if you sample with temperature 1, it gives you a lot of like not very good outputs, right? And so if you're sampling with temperature 1, you'll be exploring a very large part of the space that actually isn't very good. And so because of this, some other alternatives that you can use is you can just do n-best search to find the best outputs, or you can sample with a temperature that's not 1 or something like that, and basically create you know, a list of possible hypotheses and then normalize over them. So that's another option. And very often not using temperature 1 is a better way to do it. If you're sampling with not temperature 1 and you are potentially getting multiple outputs, you should try to deduplicate or sample without replacement, because if you get multiple outputs here, it messes up your equations if you basically have the same one in there multiple times. Cool. So this is a really simple example of how you can do minimal risk training. But now I want to get into like reinforcement learning, which is the framing that most modern works about this, Paula. One thing I should mention is there are actually other alternatives to learning from human feedback, including like margin-based losses and other stuff like that. But most people nowadays use reinforcement learning, so I'm only going to cover that here. So what is reinforcement learning? Reinforcement learning is learning where we have an environment, X, ability to make actions A, and get a delayed reward, R. And there's a really nice example, if you're not familiar with the basics of policy gradient by Andrei Karpathy, which I linked in the recommended reading, so you can take a look at that. But in that example gives an example of Pong, where you're playing the game Pong, where X is your observed image, A is up or down, and R is the win-loss at the end of the game. does anyone have an idea about what this looks like for any arbitrary NLP task that we might want to do reinforcement learning for? So what is X, what is A, and what is R? Pick your favorite task. Anybody? Yep.
A could be the next person.
Or what's X first? Yeah.
Like, where you have generated profile.
Okay.
And then A is the next person.
Okay.
Or it could be like the button the user, like whether or not you're auto security.
Okay. Yeah, I think this is very close. Just to repeat, it's like X is what you've generated so far, A is the next token, and R is the button that the user clicks about whether it's good or not. I think that's reasonably good, although I don't know if we'd expect them to click the button every token we generate, right? So it might be that X is the conversational history up till this point. A could be a next token generation, and then R is a reward we get at an arbitrary time point. It might not be like immediately after generating the next token, but it might be later. And that's actually really, really important from the point of view of reinforcement learning, and I'll talk about that in a second. Anyone have an idea from, I don't know, code generation or translation or some other things? Yeah.
For code generation, maybe X is the compiler or like the graphic script, and then the action is the actual code that it writes, and the reward is whether it passes in the form.
Yep. So X could be the compiler. It's probably the compiler and all of the surrounding code context, like what is the natural language output, and it's also you know, what is the project that you're working on and stuff like that. A, I think typically we would treat each token in the code to be an action. And then R would be the reward after a long sequence of actions. And it could be the reward from the compiler. It could be the reward from a code readability model. It could be the reward from a speed, execution speed, and stuff like that. So like one of the interesting things about R is you can be really creative about how you form R, which is not easy to do if you're just doing maximum likelihood also. So you can come up with a R that really matches with like what you want in an output. So why reinforcement learning in NLP? And I think there's basically three answers. The first one is you have a typical reinforcement learning scenario where you have a dialogue where you get lots of responses and then you get a reward at the end. So the thumbs up and thumbs down from humans is a very typical example of reinforcement learning, because you get a delayed reward at some point in the dialogue when a human presses up or down. Another, like actually more typical scenario where reinforcement learning has been used for a long time is call centers. So we've had dialogue systems for call centers. And then if you complete a ticket purchase, or you resolve a ticket without ever having to go to a human operator, you get a really big reward. If you have to go to the human operator, you get maybe a smaller reward. And if the person yells at you and hangs up, then you get a really negative reward. So this is kind of the typical example. Reinforcement learning has been used for a long time there. Another example is if you have like latent variables, chains of thought, where you decide the latent variable and then get a reward. You get a reward based on how those latent variables affect the output. So this is another example, because the chain of thought itself might not actually be good. You might have a bad chain of thought and still get the correct answer. So you don't actually know for sure that a chain of thought that was automatically generated is good or not. But that kind of makes it a reinforcement learning problem. And another thing is you might have a sequence level evaluation metric, so that you can't optimize the evaluation metric without first generating the whole sequence. So that would be any of the evaluation metrics that I talked about before. So these are three scenarios where you can use reinforcement learning. So I'm going to make a few steps through, but like let's start again with our supervised MLE loss. And that's just the log probability here. In the context of reinforcement learning, this is also called imitation learning because essentially you're learning how to perform actions by imitating a teacher. And imitation learning is not just supervised MLE. There's also other varieties of imitation learning, but this is one variety of imitation learning. The next thing I'd like to talk about is self-training. And basically self-training, the idea is that you sample or argmax according to the current model. So you have your current model and you get a sample from it. And then you use this sample or samples to maximize likelihood. So basically, instead of doing maximum likelihood with respect to the a gold standard output, you're doing it with respect to your own output. So does this seem like a good idea? I see a few people shaking heads. Any ideas why this is not a good idea? Yeah.
One is for three, and two, it's like, can't even check how it's good necessarily if you don't have some external access to it. That's good, but anyway,
yeah, exactly. So if you don't have any access to any notion what's good, this will be optimizing towards good outputs and bad outputs, right? So your model might be outputting bad outputs and you're just reinforcing the errors that the model got already. Nonetheless, like self-training actually improves your accuracy somewhat in some cases. Like, for example, if your model is right more often than not, basically optimizing towards the more often than not right outputs can actually, due to the implicit regularization that models have in early stopping and other things like that, it can actually move you in the right direction and improve accuracy. So there are alternatives to this that further improve accuracy. So like, for example, if you have multiple models and you only generate sentences where the models agree, then this can improve your overall accuracy further. This is called code training. It was actually created by people at CMU as well. And another successful alternative is adding noise to the input to match the noise that you find in the output. So if you add like word-based dropout or other things like that, this can also help accommodate these things. But anyway, so self-training is useful, but there are better alternatives if you can get a reward function. So the simplest variety of this is something called policy gradient or reinforce, or more specifically reinforce. And basically what this does is this adds a term that scales the loss by the reward. So if you can get a reward for each output, basically this, instead of doing self-training entirely by itself, you multiply it by a reward. And this allows you to increase the likelihood of things that get a high reward, decrease the likelihood of things that get a low reward. So a brief quiz here. Under what conditions is this equivalent to MLE, or essentially equivalent to maximum likelihood estimation? And so like in order to make this quiz easier, I'll go back to maximum likelihood estimation. So it looked a bit like this. You calculated the log probability of the true output. And now let me go to here. Any ideas? Yeah. When your reward equals to 1, sometimes and 0 other times. What? Any ideas? When does your reward need to be equal to 1 in order to make this equation equivalent to this equation? Yeah, when y and y hat are the same. So basically, this objective is equivalent to the MLE objective when you're using a 0-1 loss, where or you're using an evaluation function that gives you a score of 1 when it's exact match and 0 when it's not exact match. So, but that also demonstrates that this can be more flexible because you can have other rewards that are not just 1 and 0 for exact match, but you can use things that give you partial credit. You can use things that upweight multiple potentially correct outputs and other things like that. So one problem with these methods is how do we know which action led to the reward? So the best scenario is after each action, you get a reward. So after each token that you generated, you get a thumbs up or thumbs down from the user about whether they like that token or not. And how much happier they are after you generated that token than they were before you generated that token. The problem with this is that that's completely infeasible, right? Like every time after you use ChatGPT, you're not going to press thumbs up and thumbs down after each token. So in reality, what we get is usually we get it at the end of rollout of many, many different actions, and we're not sure which action is responsible for giving us the reward. And so there's a few typical ways of dealing with this. The most typical way of dealing with this right now is just not dealing with it and just hoping that your optimization algorithm internally will be able to do credit assignment. And so what that entails is essentially you give an equal reward for each token in the output. Other ways that you can deal with it are you can assign decaying rewards from future events. So like, let's say you're talking about a chatbot, for example. Maybe this is the most kind of intuitive way of thinking about it, but you have a chatbot, you have like 20 chat turns, and you have the user give a thumbs up or a thumbs down on the 20th chat turn. There you would assign a reward of like, let's say it gave a thumbs up. There you would assign a reward of 1 for the previous chat turn, a reward of like 0.5 for the second to previous chat turn, a reward of 0.25 for the third to previous chat turn, to basically say, yeah, like the user is feeling good at the moment they gave the thumbs up, and that's probably more likely due to the things that happened recently. So yeah.
We have a predetermined reward model, like we're not learning the reward.
So the reward model can be any of the methods that I talked about before. So it can be human feedback directly, like a thumbs up or a thumbs down. It could also be from a reward model that was pre-trained. You could also theoretically learn the reward model simultaneously, but you'd have to simultaneously with the model itself. So yeah, I'm going to talk a little bit about DPO, which kind of does that a little bit, but I would basically say that wherever you're getting your reward is probably from one of the things I talked about earlier today. Cool. Any other questions? Okay. So that's the basic idea. The very simplest thing that you can do is you can just sample, optimize the subjective function. This is dead easy. It's not hard to implement at all as long as you have some source of reward signal. But the problem is reinforcement learning can be very unstable, and it's hard to get it to work properly if you don't do some additional tricks. So I'd like to talk about this next. Yeah, sorry. Yeah. Yeah, the typical way is you just have an exponential decay. So you multiply each time by like 0.5 or 0.9 or something like that. From A6 to 1. Cool. Okay. So and that's one option. And sorry, just to clarify, the most common option nowadays, at least from the point of view of models, is not to decay it at all and just assign the same amount for each token. I'm not actually 100% sure what people are doing with respect to like long chat things. I think probably they're only assigning it to the current like utterance and then not optimizing the previous utterances. So like if they get a thumbs up or thumbs down signal, then they would assign an equivalent reward for all of the tokens in the current utterance and 0 reward for the previous ones. But I'm not 100% sure about that. There might be other methods that people are using. Cool. So stabilizing reinforcement learning. So stabilizing reinforcement learning, there's a lot of reasons why it's unstable. The first reason is you're sampling an individual output and calculating based on the individual sampled output. And then there's an infinity of other outputs that you could be optimizing over. For MLE, this is not a problem because for MLE, you're always contrasting the gold standard output to all of the other outputs in the space. And you're saying, I want to upweight the gold standard output and downweight all of the other ones. But for reinforcement learning, you only have a single sampled output. That output might be wrong, and that's a source of instability. This is particularly a problem when using bigger output spaces, like all of the words in the vocabulary. Another problem is anytime you start using negative rewards, because if you start using negative rewards, those rewards will be downweighting the probability of a particular output sequence. And that might be a good idea. Maybe you're getting a toxic output or something like that, and you want to downweight it. But at the same time, in addition to that toxic output, there's like, you know, a combinatorial number of completely nonsense outputs that aren't even English. And so basically you can start to diverge from the natural like language modeling distribution that you have before. So this is a big problem. So a number of strategies can be used to stabilize. The first one is, this is completely obvious right now, and nobody in their right mind would avoid doing this. But the first one is pre-training with MLE. And so you start with a pre-trained model, and then switch over to RL after you've finished pre-training the model. And so this makes a lot of sense if you're training a language model, which I assume that almost everybody in this class is going to be doing. But it does only work in scenarios where you can run MLE. And so it doesn't work if you're predicting like latent variables that aren't included in the original space. It also doesn't work in a setting where like you want to learn a chatbot. You want to learn a chatbot for customer service for a company that has like, for example, a product catalog that the language model has never seen before. And so if the language model has no information about the product catalog whatsoever, you don't provide it through RAG or something like that, it's going to have to explore infinitely, or not infinitely, but it's going to have to explore too large of a space, and you're never going to converge with your language modeling objectives. So you need to basically be able to create at least some supervised training data to train with MLE. But assuming you can do that, I'm assuming that almost everybody is going to do some sort of pre-training with MLE. The next step that people use in reinforcement learning that's really important to stabilize is regularization to an existing model. And you have an existing model and you want to prevent it from getting too far away. And the reason why you want to do this is like, let's say you start assigning a negative reward to toxic utterances, for example. If your model stops being a language model whatsoever, that's a bad idea. So you want to keep it as a language model, keep it close enough to still being a competent language model while, you know, like removing the toxic utterances. So there's a number of methods that people use to do this. The most prominent ones are KL regularization. So the first most prominent one is KL regularization. And the way this works is basically, in addition, you have two terms. The first term is a term that improves your reward. So you have your old model, where your old model is creating a probability. It has a probability here. And then you have the probability assigned by your new model. And then you have your reward signal here. And so this is basically improving the log odds, or improving the odds of getting a good reward for high reward sequences. Separately from this, you have this KL regularization term. And this KL regularization term is keeping the scores of, or it's keeping the probability distribution of your new model similar to the probability distribution of your old model. And this beta parameter, basically, you can increase it or decrease it based on how similar you want to keep the model. Another method that people use is something called proximal policy optimization, or PPO. And this is a method that is based on clipping the outputs. And we define this ratio here. So this ratio is equivalent to this here. So it's basically kind of the amount that you're learning, or the amount that the new model upweights high reward sequences. And so here we have the same thing that we had above. So it looks like this. But over here, we have a clipped version of this, where essentially what we do is we clip this ratio. This ratio to be within a certain range of the original ratio. And what this is doing is this is essentially forcing the model to not reward large jumps in the space. Because if you take the minimum, and actually, I'm sorry, I just realized I might have done something confusing here, because this is actually higher is better. So this isn't really a loss function. This is something you're attempting to maximize. So in contrast to all of the other things I was talking about before, this is something where higher is better instead of lower is better. But anyway, basically, by taking the minimum of this, you're encouraging the model to keep examining the space where you don't diverge much from the original model. And if the space where the original model was in is better than the new space that your model has moved into, you move back towards the original model. So basically, like if you had, if you learned a model, if you started learning a model that looked like it was optimizing your reward, but then suddenly the model went off the rails and it starts generating completely nonsense outputs that get really bad reward, this will push it back towards the original policy. And that's the basic idea behind PPO. In terms of what I see people using, PPO was like really, really popular for a while, but I started to see people use alternative strategies that use scale regularization. So I don't think either one of them is like particularly more popular than the others. And this one's a little bit simpler conceptually, so I like the top one. Cool. Any questions about this? Okay. And actually, one thing I should mention is all of these things are implemented in whatever libraries you use, like Hugging Face TRL, Transformer Reinforcement Learning is an example library. All of these methods are implemented there. So if you actually want to use these in practice, that's a good place to look. The next thing is adding a baseline. And so the basic idea is that you have expectations about your reward for a particular sentence. And like, let's say we wanted to translate a sentence, and we have something like this is an easy sentence in Buffalo, 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 which is a harder sentence to translate. And so we have a reward. If you're not familiar with this example, you can search on Wikipedia for Buffalo, 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 and you'll find out what I'm talking about. But there's a reward, and let's say you got a reward of 0.8 for the first one and a reward of 0.3 for the second one. But the problem is if the first one actually is really easy and the second one is really hard, getting a reward of 0.8 for the second one for like a translation or something is actually bad, right? And a reward of 0.3 is good because you're moving in the right direction. And so you basically, you have the baseline minus reward, or sorry, reward minus baseline. And this would give you a negative value for this first one and a positive value for the second one. And so the basic idea is, can we predict a priori how difficult this example is, and then adjust our reward based on that? And so that's the basic idea. You just have kind of like a baseline model. You have a baseline model that predicts this, and you adjust appropriately. There's two major ways you can do this. The first one, the baseline doesn't need to be anything. The only hope is that it decreases the variance in your reward and makes learning more stable. There's two options that I see done pretty widely. The first one is predicting the final reward. Predicting the final reward using a model that doesn't look at all at the answer that you provided. It only looks at the input, or it only looks at the intermediate states of a model or something. And so at the sentence level, you can have one baseline per sentence. You can also do it at each decoder state. And this is basically, you can do this anytime you're doing reinforcement learning by just training a regression model that does this for you based on the rewards you get. The important thing is the baseline is not allowed to use any of your actual predictions, because once you start using the predictions, then it's not a baseline anymore. Another option, which is relatively easy to implement but can still be effective, is you calculate the mean of the rewards in a batch. And so if you have a big batch of data and your average reward in the batch is like 0.4, then you just subtract that 0.4 and calculate your reward based on that. So that's another option that you can use. A kind of extreme example of this, of creating a baseline, is contrasting pairwise examples, or contrasting different outputs for the same input. And you can easily learn directly from pairwise human preferences, which can provide more stability because you know one is better than the other. So you essentially can be sure that you're upweighting a better one and downweighting a worse one. This is the idea behind DPO, which is a recently pretty popular model, but there's also other previous methods that did similar things. And the way DPO works is it basically calculates this ratio of the probability of the new model to the old model, but it upweights this probability for a good output, and it downweights this probability for a bad output. And so here we have our better outputs over here. Here we have our worse outputs. And it's basically learning to upweight the probability and downweight the probability accordingly. So you can notice that DPO is very similar to PPO in that it's learning, it's using these ratios, but the disadvantage of this is you obviously require pairwise judgments, and you can't learn a model if you don't have these pairwise judgments. Yeah. Yeah, so the beta term is basically a normalization term. It's a hyperparameter. For DPO, sorry, I read the paper right when it came out, and I don't remember if it's a direct derivation from the KL divergence term or not, but I think it might be. I'd have to go back and look at the paper, but basically the larger this is, the larger gradient steps you'll be taking. It also, like you'll notice there, sorry, I didn't mention this, but you'll notice there's a sigmoid term here. So the beta, the larger you increase the beta, the more small differences in these values, like it basically like stretches or shrinks the sigmoid with respect to how beefy it is. So it will affect how much like small differences in this will affect your gradients. But I think this was derived from the KL regularization term that we had previously in in this slide here, but I'd have to go back and double check unless somebody knows. So it is? Okay, good, yeah. So, I don't want to say wrong things, but I also don't want to. Okay, cool. And so then increasing batch size, because each, another thing is kind of necessarily reinforcement learning is going to have higher variance and maximum likelihood estimation just because we're doing sampling and other things like this. And so one very simple thing you can do is just increase the number of examples or rollouts that you do before an update to stabilize. And so I would definitely suggest that if you're seeing any stability after doing all of the tricks that I mentioned before, that you increase your batch size, and often that can just resolve your problems. Another thing that people often do is save many previous rollouts, because generally doing rollouts is more expensive. Doing rollouts and collecting rewards is more expensive. And so you can save the rollouts that you have done before and keep them around so you can update parameters with larger batches in a more efficient way. Cool. So that's all I have. I just realized we're exactly at time, so I should finish up here, but I'll be happy to take any questions up front for people. Thanks.